we talked about different ways to model the real world using differential equations. And so the two methods that we're going to focus on are exponential growth and logistic growth. Now, exponential growth is really nice because it's easy to solve. In fact, our next example, we'll solve it. And then for the rest of the course, you never have to solve it again. We can just go straight to that solution. So that is the benefit of exponential growth. But the big con is it's not realistic. It works really well for small values of time, which also corresponds to small populations. But as time goes on, this exponential growth model doesn't have any limiting factors. So the population will just grow and grow to infinity, which is a very unrealistic model. So logistic growth starts to account for some of these limiting factors to make the model more realistic. So we can add in this 1 minus p over n, where n is our carrying capacity. So imagine a lake. So we have a lake and we have 1,000 fish in it. That is the carrying capacity. If you stock it with more than 1,000 fish, then eventually they're all going to die and you'll just end up with 1,000 fish. If you stock it with less than 1,000 fish, then it'll just grow and it'll get closer and closer to that 1,000 fish. So that's what the carrying capacity, that's what we mean. And so when our population is very close to the carrying capacity, then p over n, that's close to 1. So this 1 minus 1 just goes to 0, which makes our change in population stagnate. So if you're at your carrying capacity, there is no change in population. Or as you're approaching your carrying capacity, the change becomes smaller and smaller, more stagnant. When p is equal to 0, so very small populations, then p over n behaves like 0. And so then it reverts back to just being this kp exponential growth situation. So kind of balancing when it's appropriate to use. It is harder to solve, as we'll see today. When we do one, there's a lot of algebra to it. The calculus part's easy, but the algebra, it's really long. So that is one of the drawbacks of that logistic growth. We can even model it more, modify it by adding a harvesting factor. And so this minus h, that would be, say you wanted to let somebody come fish in your lake. So you have to account for the fact that not only are the population growing because the fish are reproducing, but the population is balanced off by dying because people, they're fishing. So that's kind of the idea, big picture behind these growth models. So let's do an example. And I think I am on my morning lecture notes. Oh, I see what I did. Okay. So when you're told in a word problem that the rate of change of your population with respect to time is proportional to the size of the population, the word problem is not going to just come right out and say, hey, this is an exponential growth problem. It will be worded very similarly to the sentence here. And so rate of change of population with respect to time, that is dp dt. And it is proportional to the size of the population. So proportional, that's the K, and P stands for the size of the population. So solving this, we can use a technique called separating your variables. And the idea is that you get all of your P's on one side of the equal sign, and you get everything without a P on the other side of the equal sign. So we want to multiply both sides of this equation by dt, and that gives us the k dt, and we divide both sides of this equation by p. Then once you have it in that form, this is just regular integrals, so you can integrate both sides. The integral of 1 over p with respect to p is the natural log of the absolute value of p, and on the right-hand side, integrating k is just some number. The integral of k is kt plus c. I know why I sound funny. Okay. Now you should be able to hear me better. Is it too loud now? No, you're still good. Okay, it's so different. I think I'm in the right where the sound is pointed. Okay, so we have the absolute values. And if you think back, an absolute value of x, that is just equal to plus or minus x. So anytime when we're integrating, and this will be often when we're doing these separable differential equations, and we have these absolute value signs, then to get rid of them, we have to balance it by putting a plus or minus on the other side of the equal sign. So p is equal to plus or minus e to the kt plus c. And then using your exponential rules, you'll want to brush up on those because we'll use them a lot this section. We have a rule that tells us e to the a plus b is equal to e to the a times e to the b. So we can break up the exponent here into two separate terms, and then we can sub in a in place of the plus or minus e to the c, just because it's a lot easier to deal with an a than it is to keep writing down over and over again the plus or minus e to the c. Then to find the specific solution, which here we're calling it p naught. So at time t equal to 0, we're calling it p naught. But in general, you'd be given a number. You'd be told the initial population is 100. And so that would be the value you sub in for p naught. When we sub in 0 into our equation here, we get back a e to the k times 0. And e to the 0 is 1. So this simplifies to a. And we're told initially that p of 0 is p naught. So that gives us a is equal to p naught. The specific solution to a differential equation is a solution that corresponds to some value. So you have some point to anchor it. And in this case, when p of 0 is p naught, then the solution to the exponential growth model is p equal to p naught e to the kt. So anytime now that you see an exponential growth word problem, you don't have to go through all this work. You can skip straight to this formula right here. Because it is just that common. Other common forms, they tend to change the variables to suit the situation. So if we're talking about half-life, radioactive decay, instead of P for population, it switches to Q for quantity. Finances, it's generally A for the amount and P not for the principal amount, your starting value of money. And then R would be your interest rate. And then for y of t, this is just a generalized form of some standard equation that's in terms of y and t, or could be in terms of y and x. But generally, that's the initial value problem kind of variables there. So let's do an example. And I realize I did copy over my morning notes. So let me work my way backwards here. I think it looks the way it should. Okay. So we're given the rate at which the number of bacteria in a certain colony of bacteria increases. So that is the rate of change of the population with respect to time. That's our dp dt, is proportional to the number of bacteria present. So that gives us our setup of dp dt is proportional to the population, which lets us know that for our solution, we should just start with p of t equal to p naught e to the kt. Okay, so that's our starting point. We are given two pieces of information. We're told that initially there's 300 bacteria present. That's our p naught. Since at time equal to 0, that is our starting value. And then we're also told 2 hours later, p of 2 is equal to 500. Oh, I put that in the wrong spot. And that's enough information. We need 2 data points in order to solve our differential equation, in order to solve for P naught and K. So we sub those in, and then we can solve for P. The first one is easy. We put in the 300, and P of 2 then is equal to 300 e to the kt, but now we're letting t equal 2. And we are given that is equal to 500. And now we can solve for k. Let's divide both sides by 300. E to the 2k is equal to 5/3. And then taking the natural log of both sides and dividing by 2, we get that k is equal to 1/2 the natural log of 5/3. We sub that back into our initial equation. P of t is equal to 300 e, and in place of k, we have 1/2 the natural log of 5/3. And that entire quantity times t, and that's all in the exponent. On the side here, I showed you a different way algebraically to solve for your k. And so either way is fine, whatever you're most comfortable with. I find I just out of habit tend to just solve for k by taking the natural log of both sides. These are the same solutions though, even though they look different. We would just have to do a little bit of manipulation in order to make this equation look like that one, but either one is fine. So it's pretty easy, pretty straightforward. The problem, the reason that we can't do this all of the time is because as t is approaching infinity, the population is also approaching infinity, which we know can't happen, or we'd be overrun. And so we need some other methods to solve these differential equations. And that leads us into our separation of variables. So I'm going to skip over the opening slide. We'll come back to that warm up in one of our examples. I'm going to skip the radioactive decay example because it is the exact same as the one we just did with the exponential growth. The only difference now being that k will have a negative in it because it's decaying rather than growing. All right, so as we just mentioned with our exponential growth, the limiting factors make it hard for us to use in a lot of situations. So let's talk more about the logistic differential equation. There is so much information inside of this equation already. So I kind of want to pull it out and talk about first how it relates to the direction field, how you can just tell by looking at your initial population what the long-term population should do. And then we'll work our way up to actually solving the logistic equation. Okay, so when will dp dt equal 0? So we set our equation equal to 0. Kp times 1 minus p over n, and p is our variable here. So this is going to equal 0 when p is 0. And when p is equal to n. So what does that mean? dp dt, it is the rate of change. So it makes sense that if we're starting with no population, we're going to stay with no population. It won't I'm missing the word, but it just won't start growing out of nowhere. Spontaneously grow, there you go. So if we start at 0, we stay at 0. The other time where we stay at 0 is if we're starting at n. If we're already at that perfect carrying capacity, then there's no growth, there's no decay. That is the solution forever. And that has a very specific name. It's called an equilibrium solution. So you'll see in web work, and in workshop tomorrow, it'll say find the equilibrium solutions. And that's just math speak for set the derivative equal to 0. When is dp dt negative? So in what situations will the growth be negative or declining? If you think about our fish model, it makes sense if we're overstocking the lake, then that population will decrease until we reach the carrying capacity. Algebraically, if we have our population greater than n, then the population will continue to decrease towards n. It won't actually reach n, but it will become infinitely close to n as time goes on. And when the initial population, when p naught is between 0 and n, then that means we're in a growth situation. The population will continue to grow, but unlike the exponential model where it would just grow forever, here it has an upper bound of that carrying capacity. So the population will continue to grow as it gets closer and closer to n, but it won't cross over n. And that's what's nice about the logistic differential equation, is that it does have that limiting factor. Okay, so let's make this a little bit more concrete by sketching a direction field. Once we have the direction field, then we can sketch in our equilibrium solutions and I'll do the equilibrium solutions first, but then we can sketch in the initial condition, p of naught equal to 20. In fact, once we have the direction field, we could sketch in as many initial conditions as we wanted. Okay. So starting with our equilibrium solution, in this case, when we have 0.6p times 1 minus p over 70, that's going to be equal to 0. When p is 70, and also 0. Zero is our trivial solution. It's not very interesting. So that is our equilibrium solution. And as we talked about on the previous slide, when dp dt is negative and when dp dt is positive, if our initial condition is starting between 0 and our equilibrium solution, if we just plugged in any number into our differential equation between 0 and 70, we get back a positive number. So that means that the slope field will have all positive tick marks. Similarly, when we are starting above 70, we can plug in any number that's greater than 70, and we'll see that our differential equation, our change in population is negative, is decreasing. And so those tick marks are going to, the slope will eventually just increase or here decrease until you get closer and closer to that equilibrium solution. Now, we know from Monday that we can plug in different values for p, and whatever we get back, that is the slope of the tangent line at that point. So if we plugged in, this looks like maybe it's close to And we could just plug in any value. If we plugged in 40, then we would find whatever this slope is, that's what we would get back for dp dt. And so you can fill in the first column. A little laborious, but you can do it. But the good thing is that this is only in terms of p. It's not dependent on time at all. So this column, as t is increasing, it doesn't change. That's what we call an autonomous differential equation, by the way. Just throwing that out there, because you'll hear it in differential equations next semester or next year. An autonomous differential equation is one where it is only in terms of the one variable and not dependent on time. So when we're sketching that slope field, that means we can just repeat what we already have. Because as we move across for any individual t value, the slopes are always going to stay the same. So repeating on a grander scale, we start to get an idea of what the solution looks like. So we could plot any point along the vertical axes and then just connect the dots, and we would know what the solution looked like as t was approaching infinity. And this is a very simplistic model, so you can kind of look at it and say, well, that's obvious. Why do I need all that information? But it does scale up very nicely, where you can have quite a few equilibrium solutions. And then it is nice to know how the population is changing based on where you are above or below those equilibrium solutions. So we want to draw the solution corresponding to p naught equal to 20. So that is when t is 0, our population is 20. And to draw that solution, we're just tracing sort of the best we can along these dots. And really the only thing that you have to be really careful about, which I kind of just hit, is that you don't hit the equilibrium solution at any point. So you don't want to hit it and you don't want to cross over it. You just want to get infinitely close to it. Here I have it drawn a little bit better. And it does look like it's hitting, but that's just because my scale on my y-axis is from 0 to 100, and on my t-axis is to 10 years. So if we zoomed in, you would see that it never is approaching, that it's never hitting the equilibrium solution. And as I mentioned earlier, you can draw in many solutions, many different scenarios with initial populations, and then you can get an idea if you stock the fish, stock the lake, like really overstock it, how quickly the population declines. Whereas if it's just a little bit overstocked, then the population will take a lot longer to approach the equilibrium solution. Any questions so far? Okay, so this is the geometric approach. Let's try this algebraically. And I wrote on the side the steps for solving the differential equation so we can use it as a guide when we're separating our variables. So we'll start by getting everything with a p on the left-hand side and everything without a p on the right-hand side. That gives us, in our numerator, we have a dp, and that's going to be over p times 1 minus p over 70. And that's equal to 0.6 t. I'll leave a little space here. So now, yes, it is, thank you. So now we have it in a form where we can integrate. So we'll add an integral sign to both sides of this equation. And you might recognize the left-hand side of this equation as our warm-up exercise with partial fractions. And so this is a very typical setup for a logistic growth model. So when you see that, more than likely, you're going to have to use partial fractions to separate out that denominator. For the sake of time, I am going to skip a few of the steps, but I will do the setup. So we have 1 over p times 1 minus p over 70, and those are both linear terms in the denominator, non-repeated, linear, which means in the numerator, we need to have constants. So an a over p plus b over 1 minus p over 70. And cross-multiplying, solving for a and b, the algebra is pretty straightforward there. And you find that a is equal to 1 and b is equal to 1/70. Now I'm going to do a little side work here. Make this a little smaller as well. When we sub b in, the 1 over 70, and that's over 1 minus p over 70, it's kind of clunky having those 70s in the denominator like that. So let's multiply the numerator and the denominator by 70. Our fancy way of multiplying by 1. And that will clean this up a lot. In the numerator, we just have 1. In the denominator, we have 70 minus p. And that's a lot easier to deal with, especially when we're integrating. So subbing in our values for a and for b, we have the integral of 1 over p times dp plus the integral of 1 over, well, actually we have 70 over. Oh, no, 1 over. 1 over 70 minus p dp. And that is equal to, on the right-hand side, we have the integral of 0.6t dt. I am jumping ahead. This we know how to integrate. The integral of 1 over p, that is the natural log of the absolute value of p, plus the natural log of 70, absolute value of 70 minus p. And now anytime you're integrating and you're taking a natural log of something other than just like 1 over p, you should always just do a quick mental check. Take that derivative and make sure that you got back what you started with. So if we took the derivative of the natural log of 70 minus p, we would get a 1 over 70 minus p, but then because of the chain rule, we'd have to multiply by -1. And so this is not the correct integral because it doesn't give us back what we started with. So we need to account for this negative sign in the middle by pulling out a negative. So I will rewrite that as a negative. And now if you worked your way backward and checked, you would end up with the integrand, what we started with right here. Okay. On the right-hand side of the equation, finally, we have 0.6t plus c. We have a natural log rule that tells us the natural log of a minus the natural log of b is equal to the natural log of a over b. If this had been addition instead of subtraction, then we'd have natural log of a plus natural log of b is equal to the natural log of ab. So let's use that to simplify the left-hand side of our equation. We have the natural log of the absolute value. In the numerator, we have p. In the denominator, we have 70 minus p. And that is equal to 0.6t plus c. And our goal here is to solve for p. So introducing an e to both sides will allow us to get rid of that natural log on the left-hand side and leave us with just the absolute value of p over 70 minus p. Equal to e to the 0.6t plus c. That's all up in the exponent, the 0.6t plus c. And that is equal to, we have an exponential rule that tells us e to the a plus b is equal to e to the a times e to the b. So we can rewrite this e to the 0.6t plus c as e to the 0.6t times e to the c. And just out of convention, we put the constant first. So we can write this as e to the c times e to the 0.6t. To get rid of the absolute value signs, we have p over 70 minus p is equal to, and to balance out the fact that we just lost the absolute value signs, we put a plus or minus in front of our e to the c, in front of our constant. And because that's a little clumsy to keep writing over and over that plus or minus e to the c, we can let, and this is in blue intentionally, let a equal plus or minus e to the c. And that makes our equation just a lot cleaner. A e to the 0.6t. And now we get into the algebra part to solve for p. Where are we? We want to multiply both sides of this equation by 70 minus p. And I'm writing these steps out because it is very formulaic. So when you see similar problems, you can use this as a reference. You'll have it step by step. So multiplying through by that denominator gives us p equal to, we have 70 minus p times a e to the 0.6t. And distributing the ae to the 0.6t over the parentheses, we have 70a e to the 0.6t minus a e to the 0.6t times p. Okay, now we have p's on both sides of the equation. So let's get all of our p's on the left-hand side. And I should add, actually, we don't have any terms on the left-hand side that don't involve p, but if we did, we would move anything that doesn't have a p to the right-hand side. So And when we do that, we have P plus P, I'll switch the P and put it in front. PA e to the 0.6 t, and that's equal to 70A e to the 0.6 t. And if we've done our job correctly, then we should be able to factor a P out of the left-hand side. So we have P times 1 plus A e to the 0.6 t equal to 70 A e to the 0.6 t. Solving for P, finally, we can divide both sides of this equation by 1 plus A e to the 0.6 t. We have 70A e to the 0.6 t over 1 plus A e to the 0.6 t. This is our general solution. We're given an initial condition. We're told that P of 0 is 20. So let's sub that in and solve for A. P of 0 is equal to 70A e to the 0 is 1, so times 1, over 1 plus A. And that is equal to 20. Solving for A, the same idea as we did when we solved for P, only it's much easier now. Let's cross multiply by the 1 plus A and distribute that 20. So we have 70 is equal to 20 times 1 plus A, which is 20 plus 20A. Let's subtract 20 from both sides of this equation, giving us 50 is equal to 20A. And solving for A, we have that A is 5 halves. Did I say 5 halves? Thank you. I knew it was off. I lost that A, as she said, next to the 70, and that makes it now flipped. So let's subtract 20A from both sides of this equation, giving us 50A equal to 20, and solving for A, we have A as 2/5. So then we sub that into our general solution. P is equal to 70 times 2/5, that simplifies to 28, e to the 0.6 t. And that is over 1 plus, subbing in for A, we have 2/5 e to the 0.6 t. So now remember that our initial population, it's below our equilibrium solution. So we would expect that as t goes to infinity, this population should approach our equilibrium solution of 70. So let's evaluate this limit. I'll box this. This is our solution. All right, so looking at the long-term behavior, say in the long run, the limit as t approaches infinity of our initial condition, our specific solution. Right now, as we have it, if we let t go to infinity, then in the numerator that's growing without bound, in the denominator, it's growing without bound. So we have an indeterminate limit. So to get rid of that kind of infinity over infinity, let's multiply the numerator and the denominator by e raised to the negative 0.6t. And that gives us the limit. I think I can actually do it over here. That gives us the limit as t goes to infinity. In the numerator, e to the 0.6t times e to the negative 0.6t, that is equal to 1 times our 28. And in the denominator, we have e to the negative 0.6t plus 2/5. Now, e to the negative x has that general shape, kind of like that. Which means that as t is going to infinity, this e to the 0.6t, this e to the negative 0.6t, that is going to 0. So we have 28 over, I'll sub in a 0 to show the behavior of e to the negative 0.6t plus 2/5. And when we simplify that, we get 70, which is what we wanted to get, which gives us sort of a little added confirmation that we solved this correctly. Questions on this? Okay, I want to talk a little bit in our last few minutes about mixing problems. So this is a typical type of mixing problem. It involves a tank that's filled generally to capacity or towards capacity, and it's a thoroughly well-mixed solution, which allows us to simplify it down to a Calc 2 level. So it's entering at a fixed rate, and then it's leaving at a possibly same rate, or it could be a different rate. And our goal is to find an equation for the amount of salt Y in the tank at time t. And so to think about how to set this up, we have dy dt. Am I good? That is our change in salt with respect to time, and that's going to be equal to the rate of salt in minus the rate of salt out. And now think of the units here. So we have dy dt. So our units should be in, let's see, we're measuring y in kilograms. So this should be kilograms per minute. And that helps us keep everything straight, because if at any point we aren't getting back kilograms per minute, that means we subbed something in wrong along the way. So now the rate of salt in that is the concentration of salt I'll just finish this one line, times the rate that the solution enters or drains. In this case, it's entering. So rate at the solution enters. And so in our problem, we're told that the concentration of salt is initially 0.08 kilograms per liter. And the rate it's entering at 50 liters per minute. And I'm just going to point out that the units cancel out the liters, and we are left with something that is in terms of kilograms per minute, which gives us that added peace of mind that we are putting the correct pieces together. I'll post a video on this, and then you will do one in workshop as well, so you can use these for reference, and then the finished completed notes also. Have a wonderful day, guys. I will see you tomorrow at the exam.